We are discussing the operating system concepts. In this, we will continue with our discussion on the introduction. So we'll see about the operating system structures. So what is the objective today? We need to describe the services an operating system is going to provide to us, that is the users, the processes and other systems. And we'll also discuss various ways of structuring an operating system and how this operating system they are installed, customized, and how they boot. And also we will see various aspects like how the view which focuses on the services that the system provides, and the users and programmers, what interfaces are available to them, and also the components and their interconnections. And we'll see the viewpoint of users, programmers, and operating systems designer. So operating system services, there are various services this operating system provide to us. It provides us an environment so that we can execute the program. It provide us to debug the program. There are various other aspect which makes our program run, and that is the services which operating system provide. So one set of operating system services that provide function helpful to the user. First of all, we have user interface. That means the user interface can be the interaction between user and with the system. So you can have a CLI, that is a command line interface. You can have a graphical user interface, or you can even have a batch interface. So in program execution, the system should be able to take the program, load it into memory. Once the program is done, it should take the program out of the memory. It may be able to execute it abnormally or stop it abnormally. Then input-output operation, that is what input-output devices are connected. There are specific functions being required. And apart from that, the efficiency and protection with respect to input-output devices are very important. Then we have file system manipulation. We need to delete, create, write, read files. And when we have message passing, when there are various processes we are working, we need to have a shared memory, or even we can pass the message. This is all done by operating system. Then apart from that, nothing is perfect, so there will be errors. How to take care of the errors, how to solve it, how to efficiently manage it, this is the error detection and then protection. There are another set of operating function. Now this exists to ensure efficient operation of the system. One set we saw, now we have those functions which will ensure the efficient operation of the system by itself. For example, a resource allocation. When we have multiple user installed, then whom to give the resource, how to give the resource, and how to set the request and release. Then accountant, operating system is also an accountant to keep track of which users wants what, how many resources have to be given, and the statistics also. Then we have protection and security. Everything, whatever you are doing, we have to have a protection and security. That is protection which involves ensuring that all access to the system's resources is properly controlled. The security means authentication. We don't want any invalid access attempts, and even if it is there, we need to see the weakest link in the chain, because the weakest link is the link which is susceptible to protection and security threats. So using the operating system interface, the way you interact, it can be command line interface, it can be graphical user interface. So command line interface, that means you have certain commands. There are specific commands like you can manipulate, create, copy, print, execute files, and there are two general ways to implement these commands. These are command interpreter, self-contains code to execute the command, and there can be commands that are implemented through system programs. Then we come to the graphical user interface. You might be working on Windows, that is a kind of graphical user interface. So no entering of commands, but the use of mouse based window or menu based system, as I am using it right now. So the mouse pointer is nothing but, you have an icon. So this is nothing but a file. So when you click it, a program is invoked. Now system calls. See, operating system does everything with respect to the system calls. So all the application developers, they design programs according to the API, application programming interface. All these are there, various APIs are available. And what is the benefit of API? When you use the API, the program is portable and we have the interfaces. We just have to pass the parameters and we get the value out of it. So we don't have to worry about the internal details. Then we have runtime support. We may have certain library which are already included that provides a system call interface that may link the system calls to the operating system, and this works along with the API. See, this is where you are user. Now whenever you say open, this is your user mode. Whenever you say open, you go to the kernel mode. Now in this kernel mode, this open, there is a proper function, and this is the implementation of the open system call, and this is how the things work. So system call, they may occur in different ways in different computers. I'm saying that different computers may have different type of system calls, and three general methods are used to pass parameter to the operating system. It may be via register. You can have a block or table of memory and the address is passed as a parameter in a register, or you can have also a stack. You can use the stack, which is also possible when parameters may be pushed and popped out of the stack by the operating system, right? So there are various type of system calls. We are going to take each and every one of them. So there are 6 major categories of system calls: process control, file manipulation, device manipulation, the information maintenance, the communication and protection. So what is process control? Whenever we deal with the program which is under execution, we are dealing with process. So when a process is going on, then there are certain various things that can happen. The operating system must transfer control to the next invoking command interpreter, and then command interpreter will read the next command, right? Next command in GUI system, there may be a window that can pop up that will request action from the user, and in terms of batch system, the command interpreter terminates whole job and it will continue the next job. See, batch systems makes use of control card system, right? So a process, whenever a process is there, the instruction has to be loaded into the memory, and once it is done, it has to be taken out. So it forms a quite of a task whenever process is going on, because there are various processes which are going on. And one more question arises. The question is, where does the control goes after you have new program or program is terminated? It should go to the operating system. We have the programs which may run concurrently also. When the programs are running in concurrence, means they are concurrently running, then whom to give the priority, maximum allowable execution time, then the termination process, all this has to be seen. Then the waiting event, if someone is waiting, the process is waiting, then we ought to have a signal event also. And if some critical section is there, then acquiring log, releasing log has to be there. So the system calls in this case are end abort, load execute, create process, terminate process, get process attributes, set process attributes, wait for time, wait event and signal event, and allocation and freeing of the memory. Then we have file management. Now this file management, these systems deal with the files. So file needs to be created, file needs to be deleted, file needs to be given some access. So the system calls here is create file, delete file, open, close, read, write, reposition, get file attributes, setting the file attributes, moving and copying of the file. Then device management. See, every device, or you can say a resource are needed or they are required by the process to execute. For example, main memory, disk drives, access to files, there are various other things which are required. So if the resources are available, which process has to be given what resource? The process which has completed has to return the resource also. When you are dealing with the multi-user environment, then you ought to stop the deadlock conditions or unauthorized access or prolong access. And the device has to be closed and opened. First of all, it has to be opened. Then after the work has been done, they are being closed and made again available to the operating system. So the system calls here is to request the device, to release the device, to read, write and reposition, to get the device attributes, to set the device attributes, and then logically attach or detach the devices. Then we have information maintenance. There are so many form of information there are there, like the system calls to transfer information between the user, program and operating system. We have information like time and date, version number, the number of concurrent users, the free memory or disk space, right? Debugging information is also required to debug the program. The system calls for this is getting the time or date, setting the time or date, getting the system data, setting the system data, then getting the process and the file and device attribute. Then communication. So two common models of interprocess communication are there: message passing model and shared memory model. So what is this message passing? See, when we have very small amount of data, this is good, easier to implement. So the communicating process, they exchange messages with one another to transfer information, and these messages are exchanged between process either directly or indirectly through the mailbox. Then we have shared memory. In this, the delivery is quite faster, and process, they use shared memory. Shared memory create and shared memory attach system calls. These are the two system calls in order to create and gain the memory owned by other processes. Okay, so the data is not controlled by the operating system but the communicating process. Even the shared areas, the synchronization, all is done here. The system calls here is create, delete, communication, connection, sending and receiving of messages, then transferring of status information, attaching or detaching the remote devices. Then protection. Now, in order to control the access, we need to provide a mechanism to control access to the resource provided by the system. Especially when you are dealing with or working on internet and networks, protection becomes very important. So the system calls here is get file security status, set file security status, allow user, deny user, set file security group, like that. Then we have system programs. They are also known as system utilities. They provide a convenient environment for program development and execution. So they are divided into different categories like the file management, in order to create, delete, copy, rename, print, dump, list and generally manipulate files, directories. Status information like the date, time, disk space, number of users and similar status information. Then have file modification. We have various text editor that may be available to create, modify the content of the file which are stored on the disk or tape. Then programming language support like compiler, assembler, interpreters, and then for loading and execution, loaders, relocatable loaders, linkage editors, overlay editors, also the debugging system. Then when it comes to communication, then as we just saw, the program that allow user to send message to another screen, browse the web, send the email. So when we are designing and implementing an operating system OS, there are certain problem or there are certain things which has to be seen, designing and implementation. So this problem is not solvable, but we have various approaches. We really have various operating system. So the internal structure of different operating system, they may vary widely. This totally depends on the goals and specification you are. There can be systems which are only dealing with RTOS, that is operating system, real-time operating system. There may be general purpose operating system. So these are affected by choice of hardwares also. What are the type of systems you are going to use? So user goals and system goals, these are very important. That is, if you are making an operating system has to be made just to solve one purpose, or it has to be easy, reliable, safe and fast. The system goal is you need an operating system to be easy to design, implement, maintain. It should be flexible, reliable, error-free and efficient. And what is the important principle to participate? See, one is policy, the other is mechanism. So policy says what will be done, and mechanism says how to do it. So the design goal, as we just saw, first we have to define the goals and specification, that is the convenience, reliability, speed, flexibility, efficiency. Then what are the mechanism and policies? Just we have seen the mechanism determine how to do something, policy says what will be done. So we need to have a clear separation of the policy and mechanism. This is very important for flexibility, and these policies may change over time, but the mechanism should be general. Implementation, operating system you want to implement, you can implement in higher level language like C, C++. Previously the operating system were implemented in languages which are close to the hardware, like the machine language, and after that the assembly language. Now we can there are various operating systems that are implemented in the high level language. Now there are advantages also, disadvantage also. Advantage is the development is faster and the OS is easier to port from one system to another, but there are disadvantages also. The speed is reduced and the requirement also increases. Then operating system structure, they may have simple structure just like MS-DOS and Unix, they have very simple structure. The layered approach can be there. The OS can be broken into layers. Lowest may be the hardware and the highest may be the GUI. I'll first show you the diagram and then I'll go back again. This is the lowest level hardware. You have various layers here. So this is the layer where you are performing. So what I'm suggesting here is a typical layer has routines that can be invoked by the higher ones only. Means the higher one will invoke here. So the advantage is here is the modularity, which may simplify our debugging when any problem comes. But the layer doesn't need to know how this lower layer works, right? How it is implemented. So the problem here is layers can use only lower ones, so they must be well defined, and layer implementation, they are less efficient than other types. But nowadays the thing is that we are making layers as less as possible. Then microkernel approach is that, see, we will take the minimum of what is being required and others we transfer to system and user program. So the smaller kernel, they provide minimal process and memory management. So what are the advantages? You can extend the OS. The OS is easier to port. The reliability is high. And the main function of this microkernel is to provide a communication facility between whom? Client program and the other services. Okay. For example, if a client program wants to access a file, it needs to interact with the file server indirectly through the microkernel. For example, I'll give you an example. QNX is a real-time OS RTOS based on the microkernel design. Then we have Windows NT. This uses a hybrid structure. Then modules. This is also a type of when you can design in the layer or microkernel, you have modules also. So most modern operating system, this system implement kernel modules. These are based on object-oriented approach, and each core component is separate and each talks to other over certain interfaces, and each is loaded as needed with the kernel. So these are the modules, different modules, and they are dealing with the central core kernel. So similar to layers, but it is quite flexible. Then we have virtual machine. I'll give an example here. See, this is a virtual machine. This is a non-virtual machine. This is a virtual machine. And virtual machine, you have in this non-virtual machine, you have processes and then kernel and then hardware. Kernel can be just assumed to be a part of our operating system. But in this case, we have hardware. Then we have a virtual machine implementation. This is virtual machine 1, 2, and like this. And we have processes, different processes which are working on different kernel and different virtual machines. See, different virtual machines. So what we are trying to say here is a virtual machine takes the layered approach to its logical conclusion, and it is going to treat the hardware as well as the operating system kernel as they are hardware. So this virtual machine VM provides an identical interface identical to if it is being a bare hardware. So operating system creates an illusion of multiple processes, each executing on its own processor with its own memory. I just showed you in the diagram. So the resource of the physical computer they are shared to create the virtual machine. So CPU scheduling can create the appearance that users have their own processor. This pooling and file system can provide virtual card readers, virtual line printers as well. And a normal user time sharing terminal serves as the virtual machine operator console. So this is how it works. Virtual machine, the concept is that various things can be run, but they are virtual. Virtual means they are seen like every operating system has a different way to work. I'll show you one more diagram. Yeah, this is VMware architecture. See, we have hardware here, then we have host operating system Linux. On top of this Linux, we have virtualization layer, and we have various applications. Some application deal directly with the host operating system. Some application only work on BSD, Windows NT, say Windows XP. So these all have virtual CPU, virtual memory, virtual devices, and these are the guest operating systems. Then we have Java virtual machine. As we know that Java is kind of a very important language, but apart from that language also it has something else. Programming language specification. Java has an API and also a virtual machine, JVM we call it as Java virtual machine. This is the Java class. This is a class loader, and this is the Java interpreter. This is the host system of maybe Windows or Linux. Now what happens here is the program class now, or any program which is Java, now it is in class. This can be run on Unix, Windows, Java, anywhere. This is how it is portable. So the Java program, this is the Java development environment, and we have a separate Java runtime environment. So in this we have Java, and the Java compiler converts it into the class, and then we have the loader which interpret it to the host system, and we have intermediate bytecode that is only understood by the JVM. Then operating system generation. See, operating system, they are designed to run on any class of machine, and the system must be configured for each specific computer site. For example, we have sysgen. This is configuring a system for some specific computer site. Okay, so the sysgen program must determine what CPU will be used, what will be the boot disk, how it will be formatted, how much memory is available, what the devices are available, the OS options that are desired. Okay, so this is the operating system generation concepts. Then system boot, as we just saw, that when the system boots, there is a bootstrap program which gives the control to the operating system. It gives the control to the operating system. So booting is starting a computer by loading the kernel, and we have bootstrap program which is in the ROM, which is hardwired. So it loads the OS into the memory. So this is a very small piece of code, bootstrap loader. So operating system must have or must be made available to hardware, so hardware can start it. This is done by bootstrap loader. So sometimes two-step process where the boot block is at fixed location loads bootstrap loader, and we have firmware that actually does that. Then let us summarize what we have seen, and we'll add some more things. Operating system operation is interrupt driven. We can have exception or trap like the division by zero or say infinite loop. All these things are the interrupts which the operating system needs to deal. Then the operation is dual mode. It can be user mode, it can be monitor mode. So mode says what? User mode is your mode, monitor is actually system mode. So this monitor, a mode bit is added. So if it is the monitor is 0, the task is executed on the behalf of operating system. When the mode bit is 1, the task is executed on the behalf of the user. So at system boot time, the hardware starts its monitor mode. The operating system loads and starts the processes in user mode. Here it is monitor mode, then it is user mode. So whenever a trap or interrupt occurs, the system switches to the monitor mode. So this dual mode is very important because it protects the OS from any errant users or errant user from one another. Okay. Then the system call also. See, I'll show you with an example. This is user process. So this is executing, user process is executing. Now we have a system call. So it will go to trap. Here we have the mode bit at 1, because this is a user mode. It will change to 0 because now it has come to the kernel mode. Now this mode will remain 0, and when the system call will execute, now the mode bit will become 1, and then it will return to that is user mode. There are timers also. This timer ensures that control is always returned to the OS, and this prevents user program from getting stuck in some infinite loop, right? The timer can be set up to create interrupt. We can have a variable timer, that is a fixed rate clock or a timer. The OS sets the counter and it will decrement it. When it becomes 0, the interrupt will occur. So the timer can be used to prevent a program from running too long, compute the current time on, implement the time sharing. And we can have timer to prevent the infinite loop processing, hogging resources also. And for setting interrupt after specific period, operating system decrements this counter, as I just told you. When it becomes, it will create an interrupt, and then set up before the scheduling process to regain control and to terminate program that exceeds allotted time. Then we have process management. We have known that the process is what? The program under execution. So program is a passive quantity or entity, but the process becomes an active entity, because now it is running. Now it is actually dealt by the CPU. So we can have various threads also for process. We can have single threaded system which will have one program counter setting the next instruction to execute. We can have multiple threaded process. We have one program counter per thread. And we can have, typically system has many processes, not one. So this the operating system, the kernel running concurrently on one or more CPUs, this is also possible. So there has to be concurrency control for process and threads. We'll be dealing and discussing these words in detail. Don't worry about that. So these processes can execute concurrently at multiplexing the CPU. And when we are dealing with process management, the operating system is responsible for what? First of all, scheduling, creating and deleting the processes, suspending the process synchronization, the process communication, the deadlock handling. All these are there, and the mechanism has to be provided. So this is the second installment, and we have just discussed the things in just a few words. And I'm sure that when we go on, every aspect will be covered in detail. So till then, just wait. Thank you so much. Take care of yourself.